I think he was going to take Orgo next year, but then he realized he's not. So, um,
Yeah.
okay. But it's good. So we can like pace according to how you want it. So it's good.
Yeah, I mean, I want to finish. I really want to hit OChem too as well. I want to
Sure. Sure.
like take this class like really seriously
We
because
can
like
like do it at your pace. Yeah. So whatever you want.
yeah,
Mhm.
because like this is like my first class I want to take because a chemical engineering major. So like, I
Nice.
really need to like keep the GPA, for my honors
Nice.
and stuff.
Perfect. Okay.
So the conjugate basis, you just remove the hydrogen, and what you
Yeah.
do. Well, I mean, like for this, like you don't need to like show the curved arrow or anything. Like I don't
Yes.
like you
We'll
can
do it
just
for
like
the mechanism. Yeah.
yeah, okay. So then you can just take the hydrogen out and then leave a lone pair with the
Right.
carbon, and then
Yeah. Okay.
yeah,
Great. So then I think you know the answer. Which one is going to be the more acidic proton?
the one with the oxygen, just because the base is more stable.
There you
The
go.
one
Perfect.
with
Okay.
the yeah,
Nice. Nice. So you got that. I think the third problem is the same concept, so we're gonna skip over that. What about the third one? Actually, that's 3.4. That's important.
yeah. So this is the one with the like you have to compare the size actually. So
Yeah, okay, you got it. Yes.
in this case, the one with sulfur would be a stronger acid
You got it.
because yeah, it's just I mean for this one I kind of use the Gen Chem trick where it's like you just look at the period. If it's like down and to the right, then it's
Yeah,
a stronger binary acid.
that is, oh,
Yeah, I
that's
don't
correct.
really
That's correct. That's
yeah,
good logic. Yeah, yeah. It's still good extrapolation from that explanation.
yeah,
Yeah, that's correct. So this is a stronger acid, sulfur SH. Strong
yeah.
acid. Right. Okay.
But like it's not a strong acid, it's just stronger like relatively.
Yeah, that's
Like
correct. Stronger acid. Yes,
yeah,
that's correct. Okay. And then
yeah.
what about 3.6?
Mm, yeah, this one's it's just oxygen is more electronegative. So the one with the OH is still it's like the same thing.
Right. So you're saying this is more acidic. Is that what you said, right?
The one with the oxygen? Yeah.
Wait, hold on.
The
Sorry. You're doing
streams
3.6. Yes. We're not looking at this because it's the same concept.
oh there, I can't see 3.6 right now.
What? Hold on. Can you see it now?
Uh no, it's like I can only see like the first sentence. Like the zoom is a little bit
No. You
uh
might have been zoomed in. Can you zoom out a little bit?
I can't can I change the zoom? Oh I can. Okay. Uh but it's like a vertical, so you can't see like the yeah, okay, that's better.
Okay. 3.6.
Yeah, for this one, since you have double, single, and the lone pair, there's resonance in the nitrogen
Mm-hmm.
on the right. So that just
Yes.
indicates that it's more stable.
Yes. More
So
stable.
that one would be more acidic, yeah.
More stable, more acidic.
Yeah.
Perfect. Okay. Next one. What about over here? 3.7.
Yeah, the top hydrogen is more stable due to resonance again. Because if you draw the conjugate base, there's going to be a
Yes.
lone pair in that
Yes.
carbon. Yeah.
This one. Perfect. More
Yeah.
acidic. What about the next one?
Mm. Yeah, again, the one on the right, just because of resonance. Double, single, and
That's
yeah.
correct. More stable. Perfect. Nice. What about this one? 3.9.
This one's interesting.
Yeah.
Oh yeah, I see the trick. It's the one on the top actually,
Mm.
because
Mm.
the one on the right doesn't have resonance because it's lone pair and then double
Right.
immediately.
Yeah. And if we were to compare the hybridization, right? The orbital,
Yeah,
what would that be
yeah.
on each of those?
So wait, like when you remove the hydrogen,
Yes.
like
Well, even with the hydrogen, what is the hybridization?
of that carbon, the
Yes.
one on the bottom right, it's
Mhm.
one, two, it's SP two.
What about
three
over here?
bonds. That one is, oh, that one's sp3.
That's right. But I think when we compare the negative charges, we compare for the ones with the negative charge, right? So we're going to be actually, you're right. We were going to be looking at the negative charge of that carbon with the negative charge versus these two.
Yeah, I mean, but either way, like the textbook said that the orbital rarely rarely comes before the resonance. Like
Okay.
resonance
Okay.
usually
Is
precedes.
that's
Yeah.
correct. That is correct. But here, what about the atom though? What about atom? What did you say about the atom? Does it have a comparison for an atom? Atom versus
No, because
resonance.
it's the same atom, so you it can't be atom.
No, I
It's the same
said
carbon.
that's true. What if it was like actually orbital versus um actually electronegativity? Or so in this case,
Yeah,
like orbital versus like atom, right?
yeah. So ARIO is already in order. Like the acronym, it already ranks it in order.
ARIO. So, but that's not true though, right? Because if we think about, I don't know if that example is over here or not, but if we actually think about this hydrogen versus CH3NH2 hydrogen, okay, then
Wait, I can't see.
oh, hold on, well, it's coming. I think there's a lag here for sure.
Oh, okay, okay. Yeah, the textbook did give one example and like how
Okay,
the orbital, like what how there are exceptions, but it just said that in general, like there are rarely ever
okay,
exceptions to that.
okay.
Yeah.
It's possible then. So I think maybe they said that this is the order that's followed, but that's not always true. It might be generic that this is the order that's followed because, like in this case, right? CH triple bond CH. This carbon over here is sp hybridized carbon. And okay, so my internet has been acting up. So if you hear me like chopping out, just let me know because then I'm collecting feedback for this internet. I have to like switch it to another carrier or provider if that happens.
Okay.
Yeah. Okay. So then
Yeah.
you've got that sp hybridized carbon versus nitrogen, right?
Yeah.
So now, even though nitrogen is more electronegative, but this carbon over here is
It's
actually
more stabilized.
more hybridized. Exactly, right. The negative charge over here is more stabilized. It's
Yeah.
even though the
Because it's closer to the
is,
nucleus.
yes, exactly. So it becomes more
Yeah.
electronegative, right? That's like the
Yeah.
explanation for hybridized orbitals, that they're more electronegative, so the electrons are closer towards the atom. Okay, so this is more electronegative or acidic is what I was saying. So then, okay, over here, here's what I wanted to mention, that this is important. I think we didn't cover hybridization concept, but this is what this hybridization over here, we are thinking that it's sp3, but with the negative charge. Actually, the hybridization here is sp2. The hybridization over here is also sp2. And the reason for that is that this is able to undergo resonance. And when
that's why.
Right, that's why every time it does that, right? Even though it's a single bond, it actually is not really a single bond, it's actually a double bond.
Yeah, yeah. That's the one thing that I read in the resonance chapter that we did not cover.
Right, that's correct. So if you really think about like the previous page over here, right? This nitrogen is also, because it's able to do that resonance here, the hybridization of that nitrogen is also sp2.
Yeah.
All right. Okay. So this is what happens when the bonds, the lone pair of the negative charge is next to a double bond, the hybridization changes. So we're not really comparing it with hybridization 2 because they're the same, right? And now we're only comparing it on the basis of resonance. So one can go, the one up top can undergo resonance, so that one is more acidic proton.
Yeah.
All right. I'm just going to say more acidic. All right. So, okay, I think you can do the next one for sure. Just resonance structure. Okay, what about this one, 3.11?
Okay. Um, yeah, I mean, it should just be the one on the right. That's a carboxyl group.
Yes, yes.
So,
And why would that be?
uh, okay, so there's resonance there,
Hmm.
but there's also resonance on the top. I
Yeah.
think it's just due to induction because there's two oxygens on the right.
What about the
It
atom
grabs
itself?
the oh wait, yeah, that comes first. Yeah, the oxygen is more electronegative than the carbon.
Yeah,
Yeah,
exactly. So yeah, there is resonance, but it's in both of them. And then there is an electronegative atom on the right. So that was making
yeah,
it. So carboxylic acid, like one of the strongest organic, not strongest, but like it has a pKa of 4. In all the functional
yeah,
groups, carboxylic acid is a strong acidic functional group, right? It has an acid in its name as well, carboxylic acid, right? So
yeah.
more acidic here because of the atom. Okay. All right. So then the next is, okay, so maybe 3.13.
Oh yeah, I did this one. It's the one on the left, just because of induction.
Right. Induction. Perfect. Okay, I think I saw an interesting problem here. What about 3.14?
Yeah, 3.14. I didn't know how to do it until I searched it up, but I
Well,
figured I understood it now. It's the one
okay.
on the bottom because if you
Yeah.
because there's a methyl group on the left side
There you
of the
go.
nitrogen,
Yes.
and I didn't even think about that in the
Yeah.
beginning because
Yeah.
I looked at it, I was like, this is the same exact structure.
Yeah.
Well, how could one be stronger? And then I was like,
Right.
oh, okay, because it just like it's like less stable because of
Mm.
the negatives like really close to like the carbon and the methyl.
Yes.
I think that's why.
So what
But
is that effect called? Does it have a name?
I have, I
It's
mean,
called
it's
induction.
like yeah, that's what I thought. But like it was like
Yeah.
induction like grabs the electron density and makes it more stable. But
Right. So
in this case, it's making it less stable.
right, induction can be of two types, right? So inductive effect can be plus I and minus I. Inductive effect, right? It can be a plus I effect where it donates the electrons. But then the minus I effect is the one which withdraws the electron. And then um, the minus I effect is usually seen by electronegative atoms, right? Fluorine, nitrogen, oxygen. So when we have these atoms, right, these are electronegative atoms, so they will withdraw the electron density, right? But when
Okay.
we have atoms like mostly carbon, that atom actually donates the electron density. So then
Okay.
when we have the
Yeah.
donation of that electron density, then that effect, the result is going to be the opposite of what we are used to seeing with the acidity.
Yeah. So it becomes like the base
Exactly.
itself becomes less stable. Okay.
The conjugate base, well, yes, that's right. It'll become less stable. So then the answer is this hydrogen
Yeah.
because of plus I effect.
Wait, that hydrogen is just because of the atom, right? Nitrogen is electronegative, so it's stable.
But they both are nitrogen on both the atoms, are they not?
Yeah, but the bottom nitrogen doesn't have a methyl group attached, so there's no like I didn't really think. I just thought the top was like induction, like in a bad way, so that's why the bottom one was more stable
That's correct.
because
And that's what I said too. So, oh, sorry. So the plus I effect is acting up over here. You're right. Because the CH3
yeah,
is
okay,
donating the electron density. You're right. On this nitrogen,
yeah,
so
yeah,
it's making it unstable. So it's
yeah,
making the negative charge, making the conjugate base unstable.
yeah, okay.
All right. So then, okay, so this is a plus I effect. It's the same thing for 3.15.
Um, yeah. So the top one was most more stronger, right?
Right, exactly. This is a more
Okay.
um, plus I effect.
Wait,
Okay.
but the textbook never even mentioned that. Like
It doesn't,
when
what
did you
is,
like learn? Like it doesn't talk about like differences and like plus or
oh,
minus
and they
I.
know, Yeah, I think I learned it in my master's. Yeah, that's when I
Okay.
learned it. Probably not from, I didn't learn it from this book, textbook. Clayton probably
Okay.
should mention it. Yeah, it's like one of the most popular organic chemistry textbook, Clayton. If
Okay.
you're interested. Yeah, I think you only need that in college. You don't really need it right now. But sure,
Okay.
check it out, Clayton. It's a really good textbook for organic chemistry.
Clayton.
Um,
Okay.
yeah. Okay, compare the
Okay.
two protons. Okay, we're kind of done with that now. Okay, what about 3.17?
The most acidic. I mean, it has to be the one with the triple bond. I think it's just comparing
Yeah,
orbitals in this
right.
case.
Yeah, exactly. You got it. SP hybridization. Okay, what about 3.18? Let's just do that really fast.
3.18. It has to be the one on the right. Induction.
Yeah, exactly. Um, oh, wait, hold on. Let's back up now. Is that correct?
Uh. Oh wait, resonance comes before induction.
Yes,
That
that's
was a
correct.
bad mistake. So
Yeah,
it's one on the
exactly.
left. My bad.
Yes, yeah, exactly. That was a little bit confusing. Okay, all right. So let's do this one, 3.20.
Okay. Oh, which other ones is more
I think it's
acidic?
easy. I think it's easy.
I'm trying to think. So atom, same atom. Resonance. Do they have it? Yeah, they have resonance. They both have resonance.
They both are resonance. That's
I,
right. Now let's look for
the middle one,
possibilities of resonance. Yeah.
yeah, the middle one has more resonance, so that means it can
Yes.
delocalize more. So that means it's
Yes.
more stable.
That's right.
Okay.
So it can go here and it can go here too, right? But the one on the
Yeah.
right can only go one direction. Okay, so then this is more acidic.
Yeah. Wait, also, one point from resonance, the textbook mentioned how when
Mm.
creating resonance structures to never create new charges, but just like delocalize them. So like whenever we like split double bonds into positive and negative charges, like the textbook doesn't really like that. So
Mm.
like
So would it consider that as a resonance structure or no?
no, it wouldn't because it like one of the rules just says okay, the second rule says we want to delocalize the charge. We don't want to create new charges, and like even if the total charge is like the same, we don't want to like make
Create
new
the extra
charges at all.
charges. Really? Okay, hold
Yeah,
on. Let me double check that though, because carbonyl compound, right, always has resonance with the positive and a negative. It's considered as a resonance. Let me double check that. If that's what they're saying.
yeah.
So that is the
Because like on some of the homework problems, I would have three structures, and the key would only have two.
with like that negative and a okay, so
Yeah.
um there is no okay, so hold on. I mean, I do see their carbonyl as a positive and a negative. Is that never break a single bond, never exceed an octet of the two commandments?
Let me see if I can find it too.
Okay, so I mean, it is considering the positive and a negative on carbonyl, which is I think on page 27. I don't know if you use my textbook, right? It's on page
Well, I'm
27.
using the. I think the fourth edition is a lot more like complex, to be honest.
I think it's
I
possible. I think it's
yeah
possible that it is. Because I've seen those textbooks have some more extra problems too. Actually, I didn't
yeah.
look at that text. I can do that really fast. Um, wait, no, that's the one I sent you. The one you sent me is here. Okay.
Oh yeah, I can here. I found it. Let me just send you on Discord.
What page is it?
On the fourth edition?
Yes, on the fourth edition.
Ah, oh, okay. Let me quickly screenshot this first.
If you just tell me the page, I can get to the page.
76.
Okay.
Yeah,
76.
and it's number bullet point 2, or right above
Okay.
bullet point 2.
Okay.
Yeah.
Okay, so I got to page 76. The structure with fewer formal charges is more significant. Yeah, well, that's true though, right?
Yeah, no,
Right. If it does
it's
have
like,
less charges, it's more stable, and because we know
oh,
neutral charges are more stable too.
it's the one above that. So it talks about how like oxygen is like more electronegative than carbon, so you should never draw a resonance form in which oxygen lacks an octet. And like a lot of the problems that we were doing, we would um like create a new charge and like put like positive and negative. And
Yeah,
like
exactly. But where does it say that though? Hold on. Where does it say? Okay, because I'm reading the second bullet point, but you said the one. Okay, okay. Hold on.
like
But it's in the
it's
explanation of it.
it's the passage above the second bullet point. Like it starts with like the very first like passage on the page. That one.
So
It starts with
when
it is
it's
fairly
under is it under the okay to encounter a
it
carbon
is
atom with a
fairly
positive charge even though it lacks an octet. Yeah, as seen in the structure above, in contrast, oxygen is more like negative than carbon. You should never draw a resonance form in which oxygen atom lacks an octet. The example below, the second form is less significant. Yeah, it is less significant. That's true because it has a charge, right? We always say the most stable would be the one which is neutral. When we number them, the neutral structures are the most stable structures. But I think, hold on. Well, let me just see one thing. Yeah, okay.
yeah,
So
but it says like avoid drawing insignificant resonance forms. So
if
that's
you
why he doesn't. Yeah.
hold on. What is so like if you look at page 73, right? They have that carbonyl. You see C double bond O distributed as a positive and a negative on like a. So I think
Or the
you're
very
right.
bottom.
Yes, exactly. So I think that for carbon and a carbon, it makes sense, right? Because effectively we're writing positive and negative on carbon and a carbon. I think that would make more sense. But if you have carbon and oxygen, then it is a resonance structure because negative charge would be more stable on oxygen. So that is a relatively more important resonance structure compared to carbon and a carbon where we are just writing positive and a negative.
Okay. Yeah.
Yeah, I think you're right, but that would be true for when we have just carbon and carbons.
What about can you read the part that is directly above bullet point 3? It starts with in cases
What page?
where
What
there's an
page?
overall still 76.
Okay.
Like
76.
that's the part where I got a couple things different than the answer key. Like for those specific type
right
of
above,
forms.
in cases where there is a overall net charge, yes, as seen in the example. Oh, I see. Oh, okay. The creation of new charges is not favorable. I see it. Okay. For such charged
Yeah.
compounds, the goal in drawing resonance forms, I say, is to delocalize the charge. Okay. Relocate it to as many different positions as possible. I see it. So they're saying that is insignificant, right? Yeah. I see it. Okay, that makes sense. Yeah. Okay. So if there is a what is it called? A double bond with oxygen or nitrogen, then you can convert it to positive and a negative. But if it already has charges, they don't want you to add more charges. I see under point 4 too on 77, they said insignificant resonance. Yeah, I
Okay.
think that makes sense. Yes, that does make
Okay.
sense. Yeah. Right. Okay. I think, yeah, that's a good point.
Okay.
Because we are adding more structures, right? Yeah. And because we're adding more charges, and that would destabilize the structure too. But for like the if it's a neutral one, then you can add charges just to show that how what charge would be stable on what atom. I think that's the only thing. Okay.
Okay. Okay.
All right. So then, okay, so then we got that this hydrogen would actually be more acidic, right? Because it can form two resonance structures, but over here it's only going to form one. So what about if you look at 3.21, right? What about over here? Yeah, I think you can get this. I think you know this.
Yeah, some yeah, it's again the one on the left is an atom.
Right, you got it.
They
Yeah.
both have resonance. Yeah,
Yeah. Yes, exactly. That's correct. Okay, so let me see if we can find anything that's special, right? That we haven't covered already.
Like I mean, like for this one,
I think
there's nothing with
I
like
think we've covered all of these.
yeah, but like these are like the basic ones. Like the fourth edition textbook even covered like positive like cationic acids. And that one was like kind of it took me a couple of days to understand that part.
Wait, hold on. Actually, I'm gonna create now. I think I'll create like next worksheets from that textbook then if you think that's harder. So like what
Yeah,
for the acid-base chapter, you think
yeah,
it's harder?
I can tell you what
Okay,
section. Like
sure.
the section that wasn't in this worksheet, it's
Yeah,
section 3.5.
okay.
That one took me like I think 2 days to actually understand.
Nice.
Yeah.
Wow, 2 days. 3.5. Hold on, 3.3, okay. 3.4. And then I've got 3.5.
Yeah.
Okay. Wait,
Like
that's
the
nitrogen.
process.
That is just nitrogen and oxygen though. 3.5. Wait, which one? Is
Yeah,
it scale? Okay, maybe I'm
it's
doing
like
scale builder. That's different. So you're
yeah.
saying
Okay, I'll just like basically
what's the
it's
page?
like compare. Oh, wait, the page. The start. The first page is 116.
Okay, 16.
Yeah, but it's just comparing HA plus versus HB plus, and like I just
Oh,
thought
okay.
I've
Mm,
never like actually done this, so like
okay,
I
yeah.
was like confused. Yeah, but
Yes.
once I got it,
Yeah,
yeah, the
okay.
process is
How did you do
straightforward.
it? How did you? So here's the thing. That problem was in University of Texas, Austin. Um, yeah, yeah. I think my student was in Texas, Austin. What happened to my screen? I don't know what happened. Yes. So they were doing that positive charge problem. So how did you solve that?
It's the same exact process. It
Hmm.
depends. Like if it's just atom, if you're comparing atom, then the process is so much faster. But
Hmm.
if they're different central atoms, then you have to follow the same process, which finding what conjugate base is more stable. And
Yeah,
if
exactly.
people from UT Austin are doing this, like that's good because like, I'm trying to get in there. So
Yeah. Okay. Good. Yeah. 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 Yes. Exactly. So yeah. Um, I think my student was bio major, and he was trying to get to bio and biochem, but he found this really hard though. Like for him, it was really hard. But I think for you, it's going to be easier. I mean, if you're learning all of this right now, and they
yeah,
then but if you're a chemical engineering major, I don't know how they just kind of make it different because I think
I
their
already
chemistry
I
classes are
looked at the yeah I looked at I can send you the course outline. Basically, like the chemistry classes are like kind of the same. You take organic, inorganic, then you just then after your first or second year, then it changes to where it's more engineering based. So
okay.
it's like so yeah, biochem, chem, like pure chemistry and chemical engineering, they all first and second year they're mainly the same path, and then from
Okay.
there it'll like so lead. Yeah,
Okay.
like
Okay.
I can send it to you. Yeah,
I think, but I had another student. She was from pre-med though, but she was I mean, she didn't work with me, but like her syllabus that I saw, and then this biochem student, right? They had different teachers and different classes going on. So maybe I think maybe the pre-med track was different. is what I was thinking, because there are like different teachers teaching the material, and
Yeah.
there, I don't know if the material was different too.
Yeah.
Okay. Okay, so we've got, and so just think about, then we can get to the conjugate base, right? So then NH3 versus water.
Well, I mean, for this case, you don't have to do that because
Okay.
you're just comparing oxygen and nitrogen, and since nitrogen is less electronegative, the positive charge is more favored. Therefore, NH4 itself is just a more stable group, so it's just a weaker acid. Like, and this is a special case when you compare the two. But
The pK over here is -9. I think the pK over here is like -10, I think. So
wait, what? The pK of ammonia -9?
or oh, sorry, it's actually +9.
Yeah, okay.
And
But
what is the
yeah, it's
H3O plus?
+9.
Yeah, they said 10.6. Yeah, but I think it's in that range, 9-10, because they said
Wait, 10.6 is for the
methylammonium.
what do you call it? Alkylamine, something like that.
Right.
That's what. Yeah.
So just CH3 and yeah, okay. So
Oh,
for
yeah, so
ammonium
the-
itself, they said 9.3, right?
Yeah.
And then
And then
for
hydronium is -1.7.
-1.7. Okay, it's not -1. So then from the pKa's, we can already tell that, you know, the H3O plus is more acidic. Oh, okay. So
Yeah, but they're not. They don't give you the pKa. That's just for the solution.
of course, yes, that's right. But then even if we think about it, right, we can think about the conjugate bases. These are the conjugate bases, right? And
Yeah.
the lone pair is more stable on oxygen compared to nitrogen, just because this is more stable, right? So now instead of like comparing the negative charge, we're really comparing the lone pair. So because more electronegative atom, that is why it's more acidic. So
Yeah, I mean, for this one, like, it's just like it's a shortcut, like for like this special case. Yeah, but there's like a lot more cases where it's like the same atom. Like, there's a lot of problems where they were comparing a lot of amino groups, and then you have to use the same ARIO thing, and then yeah, it's kind of the same thing.
Okay, yes. Right. I think so. You're right. Okay, well, good. Okay, I see the leveling effect. I see the leveling effect now. Okay, good.
Yeah.
So I think for like the next chapters, I will just create problems from here, because I like this more, and I like there is more complexity to it, and they're colorful too.
Yeah.
So I like that better too. So
yeah, so
okay.
I also like position of equilibrium and like the mechanisms I got. I think I want to read the leveling, solvating, counter-ions. I'll finish the rest of the chapter today.
Okay.
So I want to read it.
Sure.
And then yeah, if we do cover it, we can quickly go over it tomorrow, like really quickly, and then we can just start the next chapter.
Sure. Yeah, for sure. Yeah. But let's. Okay. So have you understood the position of equilibrium?
Yeah, that's from Gen Chem. I remember.
Nice. I love that. Okay. Yeah. So how do we do it?
Wait, are we first doing the problems above or just this straight away?
So okay, I think these are the same problems as
oh yeah
we just did, right?
These are Gen Chem kind of.
Yeah. So I think we are done with those problems, and these are the same things we just did, right? And predict the position of equilibrium. I think we can do that. Or then we'll do maybe we can add one concept of getting to the conjugate acid and the conjugate base.
For what? Oh, for like mechanisms, like drawing the lines.
Not even that, but like if you have just like if you just have like NH3, right? What is the conjugate base of NH3?
Wait, you mean conjugate acid? NH3 is
no conjugate base. Whatever. Well, there can be a conjugate base too. What if okay, so well, you know, acid base is relative. When NH3 is acting like an acid, then we can draw out a conjugate base. So when it's reacting with species, which is something a lot more basic, then NH3 is actually going to act like an acid.
Oh, okay. Wait,
That's
is
like
that also
relative.
that?
I think that's leveling effect. I think that's what
Yeah, that is.
what they have over there. Yeah.
Okay.
Yeah.
Yeah, because I read the very first passage. I was like, nah, I cannot do this in 10 minutes. I was like,
It's
I'll
not
just
that
get
hard.
it.
It's not that hard. Yeah. So
Okay.
because it's all acid base is all relative, right? If you have something which is a lot more basic, then even a basic compound start to act like an acid. So then
Okay.
what would be the
Yeah.
conjugate base of NH3?
I have no clue.
Well, so what is the conjugate base of HCl?
HCl C minus.
Cl minus, right? How do we get
Yeah.
that? How do we get to Cl minus?
We deprotonate.
Yeah, exactly. So just remove the H plus, whatever is left over is your conjugate base.
Oh, so it's just NH2.
Yes, NH2 negative.
Oh my God.
So
Okay.
that's all you've got to know how to get to any of the conjugate bases, right? So if we had NH4 positive, what would a conjugate base for that be?
NH3.
That's correct.
Okay.
And that's what we did. Like anytime you're trying to compare acidity, you can always get to their conjugate base and then just compare the stability of their conjugate bases. That's what we do, right? So same thing, if we are doing the opposite of that. So for example, if you're going from a base to a conjugate acid. So for example, we have OH minus as a base. And if we want to draw out a conjugate acid for that, what would that be? So this time we add the H plus.
Yeah.
Right. So go from an acid to conjugate base. We remove an H plus. So what is the conjugate acid of OH minus?
H2O.
That's correct. H2O. What would be a conjugate base of this?
Okay, yeah. It's just with extra hydrogen.
That's correct.
Okay.
So you can just add the hydrogen there. Well, what would be a conjugate acid for, let's say, water?
Hydronium?
That's correct, H2O plus. So you can get conjugate acid and conjugate base for any of the species. Okay.
Okay. So equilibrium from Gen Chem, like the definition is just we always go from a strong base to a weak base, but in OChem I learned it's the more stable anion. We always move to the more stable anion.
Well, it's the same thing. Wait, stable anion. So a stable anion will make for a strong acid or a weak acid?
Wait, no, my bad. Wait, what am I saying? Never mind. Let's just go with the Gen Chem.
Let's do it. Gen Chem. Gen Chem's right. Yeah.
Yeah. Okay. So the easiest way to look at it is the main source of instability of the system is always going to be due to some sort of ion. So in this case, I see two anions on both sides of the reaction. Yeah. So I'm just going to compare the stability of both of them.
Okay.
And from here, I can already tell from just the way one of the oxygen is going to be more stable. Therefore, the system will be the equilibrium will be shifted to the right. Okay.
So in organic chemistry, right, when we look at equilibrium, we always compare the acidity. So I think when you started saying it, you were saying that we start off with compounds that are weakly acidic and so the equilibrium always move towards a weak acid or a weak base.
Yeah. Wait, one of oxygen is the stronger acid.
So hold on though. No, you're right. But you're comparing the negative charges, right? So a reaction will have an acid and a base. So what you are doing is comparing the bases. These are the bases.
Yeah.
So what I'm saying is let's compare acidity. So in Orgo, because we kind of memorize pKa's, they'll make you memorize the pKa values. So we're always looking at the acidities of acids, right? And if we just even look at these two compounds, so if by definition we learned that an acid is a compound that will donate its H plus, right? So in these two reactants, this compound with the OH actually donates the H plus and then forms the O negative, right? So this is an acid.
Yeah.
The corresponding conjugate base is this. Actually, that is a conjugate base. Okay.
Uh-huh.
And then we say the base is a compound that grabs or accepts a proton. So this is a base.
Yeah.
And this is a conjugate acid.
Yeah. But the strong acid and strong base are always on the same side. Otherwise,
So then we have
there
two
is no
acids.
reaction.
So then we have two acids, one over here and one over here. And then we say, okay, the equilibrium wants to form a weak acid. The reaction wants to form weak acid or a weak base. So we always want to proceed in a direction where we form a weak acid or a weak base. So when you go from here to here, are we forming a weak acid or are we forming a strong acid? So then effectively we're comparing these two hydrogens. We can compare these two hydrogens, this hydrogen and that hydrogen, which one is more acidic?
The one on the left?
Yeah, exactly. The one on the right is weakly acidic, right? So the reaction wants to form species that are weakly acidic because it wants to form compounds. Because if they're strong, right, they would want to react with something else. They would want to like break down its positive or give away its hydrogen. It would want to give away its hydrogen if it's strong. But if it's weak, it will sit there as it is and it will not convert to anything else. So the reaction wants to form compounds or acids that are weak. So you have to identify where is the weak acid, and once you've identified the weak acid, then we're going in the direction of that compound. So this will form products. And if you actually think about the pK of all alkanes, right, this pK is 50, and they'll make you memorize this stuff. And alcohol is around 16. So if you see how 50 is like very, and lower the pK, higher is the acidity. So over here we have very high pKa, very high pKa, yeah, so very weakly acidic.
Wait, but why can't you just compare what base is more stable?
Because in Orgo, like they just like use that as like a tool to make. You can, of course, you can, but
yeah, the textbook is just
anything?
using the base.
Okay.
Like the
base, what base?
Yeah, like the textbook literally just said compare the two bases, whichever base is more stable, it goes in that direction.
The base or conjugate base?
I mean, they're both bases. Just
so like this base versus this base, or
you just compare which one is more stable based off ARIO, and then from there, if it's more stable, it's a weaker base. And
that's correct. That's correct. You could do that too, because again, you're trying to go to form more bases. That's correct too. Yeah, we can do that.
Yeah, I prefer doing that more because, like, yeah.
I think.
Wait. I mean, technically, we're doing the same thing.
Yeah, because the reaction wants to form compounds that are weak. They can be weak acids and weak base because the concept remains the same. If you compare acidity, you can compare the acids. If you want to compare basicity, you can compare the base. But it shouldn't be strong because the moment it's strong, it wants to react with something else. And if it starts to react with something else, it's no longer the product, right? Something else would be the product. It will not stay there as is. That's why we just want to form something that is weak or stable. So I think it's the same concept, right? So this is more stable because negative charge is stable on oxygen. This is less stable because negative charge is on carbon, right? Okay.
Yeah.
What about the second?
Wait, can I ask some
Sure.
With acid base, like I've always noticed that like the weak acid and weak base are always on the same side, and the strong acid and strong base are always on the same side. Is that because of like the leveling effect, or like
that's a good
because
point.
I did this problem like in the textbook, and it was like, can water serve as a acid for the acetate ion, and the answer was no, because it's not strong enough as an acid. Like
acetate ion, right? Plus water. Okay. So if we think about it, and then what would be the product if we actually form that?
Form acetic acid and hydroxide. Yeah.
Exactly. And now compare the bases. Is OH minus more stable or that more stable?
Acetic acid is more stable.
Right? Exactly. That is why it's not going to form products, but it'll go backwards.
But like in Gen Chem, I learned that the acetate ion is just a basic salt. Like if you think about it,
It's
like it
relative
still
though. Yes, it
forms.
is basic, but then you have to add something that is more acidic in front of it for it to act like a base.
Oh, so that's why we add like HCl into it
Yeah,
to
yeah,
form
exactly.
the
Right.
salt.
Exactly. So, and when we
Oh,
form the
okay.
HCl, right? Then we have CH3COO minus plus HCl.
Oh,
Then,
but that's
right.
a neutralization reaction, which is why it was always right. Okay, okay,
Yeah.
okay.
So then we form CH3COH and Cl minus. So that's the negative charge. Well, this is the size, your atom effect, right? And that's a lot more stable compared to this acetate. That's why it goes in the forward direction. But this doesn't because it's not acidic enough.
Okay, yeah, that makes a lot more sense. Okay.
So it's all relative acidity basicity. I don't know why they're calling it leavening effect though, but it's relative.
Yeah, okay. Yeah, we can just quickly do them now.
Okay,
These
let's do
are
the second one.
hard. Okay. Uh, it's gonna go to the left.
That's correct. Perfect.
Yeah.
What about the third one?
No, I'm gonna go to the right. Inductive effect.
Yes, that's correct. More towards the right. Perfect. All right.
Mechanisms are also pretty nice actually.
Okay, great. How do we do it?
So you just draw two curved arrows basically. So in this
Going.
case, CH3O, is that methanol? What is that?
Water,
Something
HOH.
with methanol.
Oh, this?
Yeah, is that methanol?
It is a conjugate base of methanol.
Okay, yeah, okay, seen familiar. So that's the base. Water in this case is the acid, yeah. So what's happening is that the acid is going to donate a hydrogen. So what we do is we draw one arrow from the actual
Nice.
H,
Yes.
or
From the H.
yeah, actually no, that's right. I forgot. Yeah, you draw the lone pair, giving it to H, and then you draw the single bond and you give it as a lone pair.
That's correct. Really good. Yes. So the arrow always has to go from negative to positive.
Yeah,
Like that's all you have to remember, right? It's negative to positive, and then this goes from here to here.
Yeah, it's always like the lone pair can give a bond, and the bond can give like a lone pair. It's like vice versa. It can only be like that.
Nice, nice. I see what you're saying. So you can create like a bond with like the extra lone pair. You can create a bond here.
Yeah,
and
because
then
like
the bond can form the lone pair. That's correct.
Because an acid base, like this is actually a physical process. So you have to like think about it like that. But in resonance, it's not a physical process. It's just something that we use as like a tool.
That's correct. Good. Yeah, I love that. Nice. Okay.
Yeah.
Okay. What about
this?
yeah, let's do
this one,
the
like
39. Yeah.
so the lone pair is going to go to the hydrogen, and then the bond between the oxygen is going to go to the oxygen to form a lone pair.
Nice. Yeah, and then you can see that respective change in the structure too, right? The negative charge is ending up on oxygen. This was grabbing the hydrogen.
Yeah.
Okay. What about the next one?
Okay. Yeah. So NH2 is a base. It's an amino group. That's a carboxylic acid.
Yeah.
So it's a very classical like mechanism. So the lone pair is going to go to the hydrogen.
Yes.
And and then now we're just going to get an extra lone pair on the nitrogen between the bond of N and H. Yeah.
Nice. Got it. Perfect. Okay, great. Show the mechanism when you mix hydroxide with each of them, right?
Okay, so that means that they're all acids if you're mixing in the base.
Right, exactly. Yeah.
So I mean, it's kind of the same thing. It's just the lone pair goes to the hydrogen, and then again the bond between O and H just goes to the lone pair. Yeah.
Okay. So actually, let's also keep checking though, like if in all of these structures, they didn't ask, but let's also check if in all of these products are feasible products, if they're even possible to form. They didn't ask to check, and they're not. I don't think they're being very cognizant of that because it's possible that some of them might not even form.
Because of equilibrium, like the way.
Yeah, that's what I'm saying. Yes, exactly.
Okay. So that's the acid, that is the base, that's the conjugate base,
Yeah,
and that's the
yeah,
conjugate acid.
that's right.
So just compare the two bases. Um,
Yeah, which one's more
whoa,
stable?
the one on the right is more stable. So
Yeah,
yeah,
it's
that's
good.
correct.
So then we are going to form that product. Okay, what about the second one?
Uh, I think this was confusing, but I don't really think it's that confusing.
Yeah,
Um,
it's no longer that confusing. Yeah.
oh yeah, yeah. So there's the methyl group at the end. One of the
Hmm.
hydrogens is just gonna, yeah. So the lone pair goes to one of the hydrogens in the methyl group.
Where?
Wait, so I would, yeah, draw the, yeah. So
But
there's
like, is there
three.
anything more acidic? Because you're always going for the more acidic hydrogen.
Uh, that's true. Then would it be the one in the middle? Because it
Yeah,
has two resonance.
that's
Yeah,
correct.
okay.
Yeah. Yeah, I mean,
That's a
acid
great
base is a
point.
kinetic, it's a kinetic concept, right? It happens really fast. So it will always go for the one that is easily to be plugged, so easily deprotonated.
Dang. Okay. I don't think I've read that yet. Maybe. I
Yeah.
think that's in Lewis acids and bases. Yeah, when they talk about the transfer with the mechanisms. Okay. Yeah, I'll finish reading the whole thing
Wait, hold
again
on.
too.
We can do the same thing though. What I'm saying is just choose okay, so when you're here, right? What I'm really saying is that we're choosing this hydrogen over this hydrogen. Why not this hydrogen? Even though it is on the sp2 carbon, it's because we say that this hydrogen is the most acidic, and that's why we're kind of ignoring the other ones.
Yeah, yeah. Like
So
I didn't even
same
think
thing.
about like it.
Okay.
Yeah, it didn't come across like my head because I didn't read it. That's what I'm saying.
Okay.
But
Okay.
now,
I
yeah,
got
it
it.
makes sense.
Right. Yeah. So then we'll actually choose this hydrogen.
Yeah, yeah.
Right.
And then based off of that, our actual structure changes. Like I see what you're saying. Like
Right.
now that one will change. And then, do we have to draw a resonance? Like if we or no?
No, we don't have to. No, not really.
Okay, because
Um,
yeah, that would be a really bad pain. I'm not gonna lie. For-
to draw two resonance structures, those are so simple resonance structures.
No, no, it's not that. It's just that like now your problems just became
A
like
resonance problem,
three more
yeah.
steps.
They will
Yeah,
make you
like
do that in school though. I'm not making you do it right now, but they can say draw the product and also draw the resonance structure.
okay.
Okay, so we've got this
Well, I
product.
mean,
Now
re-
let's check.
yeah, yeah. So
Let's check if
yeah, of
this
course,
equilibrium is favored or not.
yeah, it's favored. It's just because now there's not even just one resonance, there's two possible resonance. No, three possible
Mm.
resonance structures.
Over
So
here, right?
it's
What about here?
yeah,
Negative
lot.
charge.
There's no resonance. So. Wait, what am I doing? The
Mm.
atom comes
Yes,
first. Oh
yeah,
my God.
yeah, exactly. There you go.
Okay, yeah. So it's not favored,
Yeah, exactly.
but
It's not.
that
So
doesn't
it's
mean it won't happen. It's just that it's really shifted to the left.
exactly. There will be a little bit of product, and if they're doing a reaction which is ending up forming water, right? And if they start to remove the water from the reaction, if they're doing
Yeah,
like
they chart layers. They chart layers
exactly, then they
principle.
can force it to form products. That's right. But right now,
Yeah.
it's only a little bit of the product would be formed. So they do like one of the Claisen and condensation reactions, and the first step is this. But then again, right, just a little bit of this is formed until a more stable product is formed. Okay, also the pK here is like 25, right? Now the pK here is around 18. So we can see how a strong acid is actually being formed from a weaker acid. So it's actually more towards the left, equilibrium towards the
Okay.
left.
Wait, do you have
Okay.
anything I could do to memorize pK values?
Yeah. Well, I have the table here. So I think they have a lot of the values that you need to know. Um,
Okay, yeah, I'll just, I mean, start trying to, just
yeah, exactly.
memorize a little bit.
Yeah. And I know you'll try to like relatively think about it. For example, you'll do alkane, alkyne, so you'll get like relative numbers in your head. And same way when you have the nitrogen substrate compared to an alcohol. Well, I think this table is not doing that, but then relative compared to where is the alcohol? Does it have alcohol here? CH3OH, right? So I think that's like a good way to compare the acidities, alcohol versus an amine, alkene, alkane, alkyne, to think about these numbers and think about, okay, where do they actually lie on the pKa scale. Water, I think water is very questionable. Like a lot of the websites will say 16, some of them will say 15, this says 14, so it's very questionable. So you can always
it's
have that range.
experimentally it's not 14. The textbook said it was like 16 experimentally.
Okay,
I don't
yeah.
know why.
So I've seen a couple different numbers in people's notes as well and the websites. Okay. But then yes, if you look at it relatively, it'll be easier for you to actually understand that. All right, let's now do this problem really fast. Plus OH
Yeah, it's that the hydrogen on the very end is the most acidic in this
right.
case.
Yeah.
So the lone pair will go there. Yeah.
Nice.
Same thing. And yeah, definitely this is feasible. Shifting to the right,
Yeah,
more stable. Yeah.
that's right.
Yeah.
Okay, yeah. pK over here is like pK4, benzoic acid, probably less than 4. It should be around 3 here. And then water 14, 15, 16, whatever we are saying. So we are going more towards the right. And also here we see resonance, no resonance. So okay.
Yeah. Also for the arrows, like they depending on like what side it shifts on, they draw one side like longer than the other.
What do you mean?
Like in this case the top arrow? No, like the equilibrium, like the
oh yeah, that's because yes,
arrows.
that's what they're saying. The forward reaction is more favorable compared to the backward. That's what it means, right?
Okay. Yeah. I was just like asking if that notation is more preferred compared to.
Okay, yes. So yeah, I mean, they can write like this and they can ask you like direction. They can ask you to predict the direction. Then you will say forward or backward. If they make you write the arrow, then you draw the arrow like that. When they're asking you to predict the arrow direction and then write the arrow, so then you write that one. Okay. So now this one is the same problem, right? But I think for your practice, you said already you practiced these problems, except these
Yeah,
ones,
I just
right?
like quickly looked at them.
Okay.
Looked at them and just like.
So for your homework tomorrow, would you get some more practice from like that textbook?
I mean, yeah, I just like read through it. Yeah, can you actually just can you like if you want to add more acid-base problems, I guess you can. But,
okay.
Can you upload the next chapter's homework too?
Oh yeah, for sure. Yeah, I think I haven't created it yet, right? So I'm just gonna create it from your textbook now because I like that better.
Okay.
Yeah.
Yeah, so I'll just like check the Google Drive like around 4 today, and like whatever's updated, I'll just like do that. Whatever it is.
Oh, okay,
if it's acid base or like
Okay.
cycloalkane,
I'll add both the things then. Acid base and cycloalkane.
Yeah, and I'll just start. Yeah, once I finish the acid base chapter, I'll just like read the next chapter.
Okay. All right. Great. Sounds good. So that's what we'll start off with tomorrow. And of course, if you have questions, we can take them first and then get into that.
Okay. Yeah.
Right. Sounds good. We'll see you tomorrow then. Same time.
Yeah. Okay.
Right. Bye now.